Hey guys, I'm going to work through the Chapter 8 test review. I'm not going to go over the scientists or the variables in the equations, but that's in the key that I've also posted on my teacher webpage. So I'm going to start down here with the problems and work through the problems with you. So number 1 says an astronaut has a mass of 75 kilograms. Calculate his weight on the moon if the moon's mass is 7.36 times 10 to the 22nd kilograms and the moon's radius is 1.74 times 10 to the 6 meters. The hint says to calculate the g, which is the acceleration due to gravity on the moon. So if you remember, our equation for little g is big G times the mass of the planet divided by the radius of the planet squared. So let me try and zoom in here. So big G is 6.67 times 10 to the negative 11th, and they tell me that the mass of my planet is 7.36 times 10 to the 22nd kilograms, and then we're dividing by my radius, which is 1.74 times 10 to the 6 meters squared. So if we plug that into our calculator, we get a little g of 1.61 meters per second squared. But the question asked what his weight was. If you remember from the forces unit, weight is equal to m times g. So we're going to do m times g, and they tell us that his mass was 75 kilograms, and we're going to multiply that by 1.61. So if you do that in your calculator, you get 121, and if you remember, we measure weight in newtons. That was question 1. Question 2 says, on the surface of the moon, a 91 kilogram physics teacher weighs only 145.6 newtons. What is the value of the moon's gravitational field at its surface? What it's really asking you is to find little g. So if you remember, little g is equal to, if we take m times g, it's equal to our weight. They give us a weight of 145.6 and a mass of 91. So we're finding little g. So we divide both sides by 91, and we get a little g that's equal to 1.6 meters per second squared. So that's the answer to number 2. Let's move on to number 3. Number 3 says, astronaut Ed, who has a mass of 85 kilograms, and astronaut Sarah, who has a mass of 50 kilograms, are training in Houston. Calculate the gravitational force between them if they are 10 meters apart. So that's our key right there, their gravitational force, which is our F equals big G m1 m2 over r squared, or our distance squared. So big G, if you remember, is 6.67 times 10 to the negative 11th. My first mass was 85, and my second mass was 50, and they tell me they're standing 10 meters apart. So don't forget, you have to square that 10. So if you plug that into your calculator, you get a force of 2.83 times 10 to the negative 9th. And we measure forces in newtons. So that's the answer to number 3. Moving on to number 4. It says the space station, which is 4.5 times 10 to the 5th kilograms, and the Soyuz capsule are 20 meters apart. If the gravitational force of attraction between them is 5.25 times 10 to the negative 4th newtons, calculate the mass of the Soyuz capsule. So our key here is it says gravitational force, so we're going to use our gravitational force equation, which again is F equals big G m1 m2 over my distance squared. They give us one mass, so that's our m1, and they give us the distance they are apart, that's our 20 meters, and they give us our force, and they want us to calculate the second mass. So if we rearrange this equation, we start by multiplying both sides by d squared. So we have f d squared equals g m1 m2, and we're solving for m2, so we're going to divide both sides by g times m1. So the equation I want to use to calculate my mass is force times my distance squared divided by g times m1. So they tell me my force was 5.25 times 10 to the negative 4th newtons. My distance is 20 squared. G is 6.67 times 10 to the negative 11th. And my first mass was 4.5 times 10 to the 5th. So if we plug that into our calculator, we're going to get a mass of 6,997 kilograms. Remember, we measure masses in kilograms. So that's the answer to number 4. So let's move on to number 5. Number 5 says, an astronaut whose mass is 85 kilograms is driving in his car, which is 450 kilograms. He turns a corner in his car going 15 meters per second. The radius of the turn is 15 meters. What is his centripetal acceleration and what is his centripetal force? So if you remember, we have two different equations for centripetal acceleration. We have v squared over r, and we have 4 pi squared r over t squared. But the information they give us is a velocity and a radius, so we want to use this equation. So we have our velocity squared, which was 15, and our radius, which was 15. So you're going to end up with a centripetal acceleration of 15 meters per second squared after you plug that in your calculator. And then remember force, we calculate F equals ma. Well, our mass is not just the astronaut's mass or not just the car's mass. Our mass is the sum of the two because they're in the car together. So if we add those two together, we get a mass of 535 kilograms. And so we plug that into our equation, 535 times 15, and we get a force of 8,030 newtons. So that was the answer to number 5. Let's move on to number 6. So number 6 says the space station is 400 kilometers above the Earth. The mass of the Earth is 5.97 times 10 to the 24th kilograms, and the radius of Earth is 6.38 times 10 to the 6th meters. Calculate the velocity of the space station as it circles the Earth. So we need to use a velocity equation. The velocity equation we have is v equals the square root of g times the mass of my planet divided by my radius. So v equals, g is 6.67 times 10 to the negative 11th. They tell me the mass of my planet is 5.97 times 10 to the 24th. And they give me a radius that is 6.38 times 10 to the 6 meters. And what we have to remember is here is Earth and my space station. So the radius I really want is this whole distance, which is going to be my 6.38 times 10 to the 6 plus my 400 kilometers. And if you remember, kilometers is times 10 to the 3rd. And then we're taking the square root of the whole thing. So when you plug that into your calculator, you get a velocity that is 7,660 meters per second. That's the answer to number 6. Oops. Moving on to number 7, it says if the centers of Earth and the Moon are 3.9 times 10 to the 8th meters apart, the gravitational force between them is about 1.9 times 10 to the 20th newtons. What is the approximate mass of the Moon? So it tells us gravitational force. That's our key word to know. We're using our F equals G m1 m2 over r squared equation. They tell us our force is 1.9 times 10 to the 20th. We know G is 6.67 times 10 to the negative 11th. And our two masses, we have one of the Earth and one of the Moon. Well, if you look back into problem 6, they give you the mass of the Earth. So our first M1 is 5.97 times 10 to the 24th. And we're solving for M2. And they give us our distance is 3.9 times 10 to the 8th squared. So we need to solve our equation for M2. So just like we did before in problem 4, we multiply our force times our distance squared, or our radius squared, and then we divide by G times M1. So to find our second mass, our equation is force times our distance squared divided by G times M1. So our force was 1.9 times 10 to the 20th. Our D was 3.9 times 10 to the 8th, and we square that. And then we divide it by, this is just a squiggle, G, which is 6.67 times 10 to the negative 11th, times my first mass, which was 5.97 times 10 to the 24th. So we put that into our calculator and we simplify, and we get that our second mass is 7.26 times 10 to the 22nd kilograms. Then number 8 says the velocity of a planet as it orbits around the sun increases, decreases as it gets closer to the sun. If you remember, we talked about things that are more massive, it makes the planets move faster, closer to them. So the answer to number 8 is going to be increase. Number 9, that's Kepler's laws. It says planets orbit around the sun in an elliptical path. And then 10, what happens to the gravitational force between two objects when the mass of one of the objects doubles? So here's our equation, F equals G m1 m2 over our distance squared. So for doubling a mass, that means we're multiplying it by 2. So we have G 2 times m1 m2 over our distance squared. So since the 2 is on top, that means that our answer needs to be a whole number. So if we double one of our masses, that means that it's going to double our force. So the force will be twice as large. I'm going to stop there, and then I'll pick up on number 11 in the next video.